Hey there, Keys Pre-Calculus kids. We are working on section 7.1 and 7.2 today. I'm doing this video because I do not want to cover this in class because it is simply review. And I think most of you remember how to do all of this anyway. But I wanted to go ahead and make sure that we've got it covered just in case. We are working on solving systems of equations. Now, so far, all the problems we've had have either involved a function of one variable or a single equation with two variables. But there are so many problems in science, business, and engineering that involve two or more equations with two or more variables. And so to solve these problems, we have to use a system or a system of equations to solve for our unknowns. So far, in your math career, you have learned this substitution method, you've learned the elimination method, and of course you've learned about graphing them. So that's what we're going to do today. We're just going to review all of these. Later on, starting on Tuesday, we're going to start learning other ways to solve systems of equations, including the Gaussian elimination method, which leads to matrices, which make it simpler, and then which leads to Cramer's rule. So we're going to solve lots of different kinds of systems this chapter. But today we're just going to review substitution, elimination, and graphing. Before we get started on it though, I wanted to remind you that a solution of a system is an ordered pair, or if you've got more than one variable, or more than two variables, it'd be a triple pair, or not triple pair, a triple, sorry. Anyway, it's a solution set for each equation that satisfies both equations. It's true for both equations. So in this case, we would have both an x and a y that satisfies both the red equation and the blue equation. And our job is to find that. And the first way we're going to do this is using the substitution method. So the way you use the substitution method is you simply find a variable in one of the equations that you can isolate, put it by itself. And it's pretty easy to do that. You can do either one, but I would pick the one that's easiest. It's pretty easy to do that with the red one here. So I would just solve this red one for y. So if I move the 2x over, then I get y equals 5 minus 2x. And so now I'm going to take this solution, what y is, and I'm going to substitute it for the y in the blue equation. So I'm going to come over here and I'm going to write 3x minus 2 times, now instead of writing y, I'm going to write what y is. It is 5 minus 2x in this system. Oops, wrong color. Get that color to work. Equals 4. Now, then we just order of operations. 3x, distribute the negative 2, so we get minus 10x plus 4x equals 4. And then when I collect like terms, I get, oh goodness, that's not an x there. Sorry about that. Okay, so I get 7x minus 10 equals 4. Now, of course, y'all are to the point where you do not have to show every step. You can do a lot of this in your head. So we get x equals 2. So once I've solved for x equals 2, I can substitute it back into any one of the equations. But since I've already solved for y, I'm going to substitute it back into this one right here, because I've already solved for y. So y equals 5 minus 2, and I'm going to substitute it back 2. So therefore, y equals 5 minus 4. So y equals 1. So the solution set for this system of equations is 2, 1. Now we can see that if we graph these two equations. Here I've come over here to Desmos and I graphed both the red one and the blue one. Now we had to put them in the form of y equals, so I had to solve each one for y in order to graph it. You can do this on your graphing calculator, you can do it at Desmos. But do you see where these two lines intersect? They come up here and they intersect The red one has a y-intercept of 5, slope of -2. The blue one has a y-intercept of -2, a slope of 3/2, and they intersect at this point right here. And that is the point 2, 1. So a system of equations, again, has a solution set that its solution will be the ordered pair or the triple or whatever it is that satisfies all equations in the system. And the ordered pair 2, 1 satisfies both of these. It's true for both of these equations. Now I'm going to take this same system, 2x plus y equals 5 and 3x minus 2y equals 4, and I'm going to solve it, just reminding you how to use the elimination method. I'm going to solve it with the elimination method to remind you how to use that. And the way we do that is we add the two equations together, and we eliminate one of the variables. But if I were to add or subtract straight down, 2x plus 3x, it doesn't get rid of an x, and I can't get rid of a y by adding straight down, so I have to multiply either one or both of the equations by a number. And if I multiply all the terms, I don't change the value of the equation, I just change the way it looks. And so I need to pick what would be easiest to eliminate. Well, I see that my y's are already positive and negative, so it'd be easy to add instead of having to subtract or to multiply by a negative number. And I can turn my pink y into a 2y very easily by taking this entire equation and multiplying it by 2. And when I do that, I'm going to rewrite the new solution underneath. 2 times 2 is, or 2 times 2x is 4x. 2 times y is 2y. And 2 times 5 is 10. So now my pink equation has turned into a green one. It's the same value, it just looks different. Let's see if I add them up. If I add straight down, I'm going to get 3x plus 4y equals 7x. 2y, negative 2y and positive 2y add to get 0. Now, if they were the same sign, I would be subtracting the green from the red, or from the blue. But because they're different signs, I could just add them, and that becomes, that zeroes out. 7x equals 4 plus 10 is 14. And so again, x equals 2. And then I can substitute that 2 back into either equation. It does not matter which one I use. Last time I used, well, I'm going to go ahead and do the pink one anyway because I could show different colors. But 2 times this 2 here plus y equals 5. Well, 2 times 2 is 4, and if I subtract 4 from both sides, then I get y equals 1. I could have done the same thing with the blue equation, and the green equation is the same as the red one, it's just bigger numbers. But I could have said 3 times 2 minus 2y equals 4, and if I multiply both sides, or 3 times 2, I get 6, and I subtract that from both sides, and I get negative 2y equals negative 2, so y equals 1. So any way I use it, I still get a y equals 1 no matter what I do. So when I change my color up here, my solution set is the ordered pair 2, 1. So I have the same answer using the elimination method, using the substitution method, or graphing. Any of them work. You get to choose what is easiest for you to use. I'm not going to dictate how you do it. Let's go through another example here. We've got 2x minus y equals 4 and negative 4x plus 2y equals negative 12. You can choose either method you want to use that we've looked at so far, either substitution or elimination. I'm going to go ahead and just do substitution. If I solve for y here, I get y equals 2x minus 4, because I moved y to one side and made it positive, move the 4 to the other side. So basically y is 2x minus 4, and then when I substitute that into the next equation, I get negative 4x plus 2 times 2x minus 4 equals 12. And that would be negative 4x plus 4x. Uh-oh, what's going to happen here? 2 times negative 4 is negative 8 equals, what did I say, 12? I think I meant to put negative 12 up here. It equals negative 12. These 4x's cancel each other out, and I'm left with negative 8 equals negative 12. That is not a true statement. That is false. Therefore, when I get down to something like this, I have to decide what's my answer going to be. Well, because this makes a false statement, that means that there is nothing that will work in the real number system. There are no real solutions, so there's no answer. There's no solution. Let me see if I can fix that. No solution. Okay. There's no real number solution in this system. There's an example on page, let's see. Sorry about that. There's an example on page 456 where you get an imaginary number. Well, if we're talking about the real number system, there is no real solution because you're solving a system that is not linear. You've got a quadratic and a linear, and they don't intersect in the real number system. Therefore, there's no solution in the real number system. I'd like you to study example 3 on page 450. I said the wrong number. Page 455, example 3. And you will see that it uses the quadratic method, or the quadratic formula, and you find that your answer is an imaginary number. Therefore, there's no solution. So if you get down to an untrue statement, and there's no, you have no variables and it's not a true statement, or you get, like, for example, a quadratic that has an imaginary number in it, then you have no real solutions, and there's no solution to the solution set, or to this system of equations. So what does that mean graphically? Well, graphically, that means that those lines they're never going to intersect, so they are parallel. And what I did is I made the red one, I solved it for y, which gave me 2x minus 4. And then the blue one, I solved for y also, but I didn't simplify because I wanted you to see where it came from. But it's 4 halves x minus 12 halves, which is the same thing as saying 2x minus 3. So they have different y-intercepts, but they have the same slope. And so they're in the real number system, they never intersect. Therefore, there is no solution. But what if I were to take this system of equations here on the left, and I changed one of the numbers? I let the blue, or the bottom equation, equal negative 8 instead of negative 12. If I were to solve this, and I'm going to solve it using the elimination method, just to show that method again. So if I were to solve this, what would my solutions be? Well, here I took the first equation and I multiplied it by 2 so I could eliminate one of the variables, but it ends up actually eliminating both, because 2x times 2 is 4x, and negative y times 2 is negative 2y, and then 4 times 8 is 2. So if I take this blue equation and this green equation and I add them together, I add straight down and I get 0 plus 0 equals 0. So I have 0 equals 0. That is a true statement. That means that there are infinite solutions. In other words, whatever solution set or order pair works for the red statement, it's also going to work for the blue statement. For example, I'll choose the order pair 3, 2. I'm going to substitute it into the pink state, or the red statement. So 2 times 3 minus 2. Is that true for the pink statement? 2 times 3 is 6, minus 2 is 4. Yes, that's true. So let me check it for the blue one. So we've got negative 4 times 3 plus 2 times 2. Does that give me negative 8? Well, we've got negative 12 plus 4. Yes, in fact, that does equal negative 8. It doesn't matter what I choose. Whatever ordered pair works for one will also work for the other because they're infinite solutions. Well, what does that look like graphically? Well, graphically over here, I've got my first one, 2x minus 4. That's the red solution, or the red the red equation. And if I put an 8 here, because 8 divided by 2 is 4, right? And that was part of my problem anyway, it was an 8. What happens? It becomes blue. It doesn't really become blue. It overlaps because they are the same line. They just look different. As an equation, you might have bigger numbers or smaller numbers, but they're the same. They're the same graph. So this system is the system that gives you infinitely many solutions. Let's look at another system. Now, I know in Algebra 2, y'all did a bunch of linear systems of equations. I don't know if you did anything that wasn't linear, but this one's not. The first one is a linear equation. The second one is an ellipse. So we are going to see if they intersect on a graph. But before we do that, let's solve it algebraically. I think the easiest way to solve this would be using the substitution method. So I'm going to solve for y here. Y is equal to x plus 3, because I just moved the x to both sides. So I'm going to substitute every y I see, or for every y I see, I'm going to substitute x plus 3 in its place in the second equation. So here we go, x squared plus, instead of y, I'm going to write in x plus 3. I'll change my color here. Squared minus 6x minus 27 equals 0. I'm going to go ahead and square this, so I get x squared plus, when I square x plus 3, I get x squared plus 6x plus 9 minus 6x minus 27 equals 0. So when I solve this down, I collect like terms, I get 2x squared. The 6x's cancel each other out. Okay, and then I'm left with minus 18 equals 0. Now there's a couple ways I can do this. I'm just, because I don't have an x variable, I just have the x squared variable. I'm going to add 18 to both sides, and I get, and then divide by 2, I get x squared equals 9. So then I have to take the square root of both sides. Now, don't forget that when I take the square root of both sides, I have two solutions. I have both positive and negative 3 that satisfy this. So I've got to substitute both of those back into an equation to solve for y. Since I've already solved for y up here, it's easy for me just to substitute it back into the pink equation. So the first one, y equals, and then instead of x, I'm going to put 3 plus 3, and that gives me 6. So I have one solution set that is the answer 3, 6, or one ordered pair, I should say. I keep calling it solution set, but I mean ordered pair. And then if I do it again, y, well, a bit blue, y equals, it's not working, negative 3 plus 3, then I end up getting a 0. So my other ordered pair is the answer negative 3, 0. So these two ordered pairs, they both work in this system of equations. So my solution set has more than one answer. It's got two answers. What does that look like graphically? Well, you should guess. What do you think it looks like graphically? All right, let's pop over and see. Now, I had to solve each equation for y. So the first one is just the line, 3 plus x, y equals 3 plus x. And the second one, because it has two solutions, both positive and negative, I needed, and I didn't know how otherwise to do this on Desmos. So, because I don't know how to do a function, I couldn't find a plus minus. So I did two of them. I did the positive one, and that's this top half of the ellipse. And then I did the negative one, which is the bottom half of the ellipse. And you can see that the line crosses the ellipse in two places. It crosses here at the point negative 3, 0. And it also crosses here at the point, well, if I move it over there, 3, 6. Yeah, oh, look, I didn't know I could do that. That is really cool. All right, so there at negative 3, 0 and 3, 6. Those are my two solutions to that system of equations. Those are the graphical solutions, but we found it also using the substitution method. It's a lot easier to use substitution when you're graphing this one than elimination because of the variables, or because of the exponents. All right, so this is a case where, because it's not two lines, you can possibly have more than one solution. If there were no solutions, that means that the line would have not gone through the ellipse. It would have been above it or below it, but they would not have intersected in any way, shape, or form. And you are going to find some problems like that on your homework. Before I let you go, we're going to look at another example, and then we're going to talk about application. So bear with me for a little while longer. So what if you see a problem like this? You're like, ugh, decimals, I don't want to deal with a bunch of decimals or fractions. You can get rid of those decimals or fractions by multiplying by, if it's a fraction, a common denominator to everything, to just each equation by a common denominator to eliminate the fractions, or in this case, because we've got decimals and everything is 2 decimal places over, in the hundredths place, I can multiply everything by 100 to get a 2x minus 5y equals 38. And the same thing for the bottom equation, 3x plus 4y equals 104. Or, because I still want to get rid of my, I'm going to use the elimination method in this case, I want to get rid of one of my variables. I'm going to choose the positive and negative variable to get rid of. The book chooses to get rid of the x variable because it's smaller, but the y variable is bigger. But I like, because one's positive, one's negative, I can just add straight down. So in order to do that, I'm going to have to multiply the top row by 400, and I'm going to have to multiply the bottom row by, hold on a second, change my color here, by 500. Let's see, when I do that, I'll go, since I've already got green here, I'll do the bottom row. So I get 500 times 0.03, and that gives me 15x, because I moved my decimal place 2 places to the right, then multiply 5 times 3 to get 15. And then I do the same thing here. 500 times 0.04 gives me 20 plus 20y, and then 500 times 1.04 gives me 520. Now, I'm going to do the same thing with the top equation. 400 times 0.02 gives me 8x minus 20y equals negative 152 when I distribute the 400 through everything. Now, if I'm going to go ahead and just solve straight down, then I get 8x plus 15y equals 23, sorry. X equals 368, because the 20y's, negative 20y plus positive 20y eliminates each other. And so then when I divide both sides by 23, I get x equals 16. And then if I were to take the 16 and substitute it back into one of the equations and solve it down, which y'all can do on your own, you can check it, whatever, you're going to end up getting y equals 14. I believe, yes, 14. I'm not going to take the time to substitute it back in. You know how to do that. So that's called back substitution, but you can do that. So the solution to this system is 16, 14. That is the solution to this system of equations. Now, the whole point to working with this system of equations is to solve application problems. And I know I told you I like to do straight math, not so much application, but this is necessary. So how do you know if you need a system of equations for application for an application problem? How can I tell? Well, there's a couple things to look at. Does the problem that you're looking at involve more than one unknown quantity? And are there 2 or more equations or conditions that need to be satisfied in your problem? And if you can answer yes to either one of those problems, then chances are really good that you've got to use a system of equations to solve for an answer. And we're going to look at problem number 62 on page 470 in your book now. practice this. It says 2 planes start from Boston's Logan International Airport and fly in opposite directions. The second plane starts a half an hour after the first plane, but its speed is 80 kilometers per hour faster than the first plane. So find the speed of each plane if 2 hours after the first plane departs, the planes are 3,200 kilometers apart. So here we have 2 unknowns for each plane. And each plane has a different direction it's going. It's got a different rate, and it flies a different time. So we're also going to have 2 equations, one for each plane. Therefore, this is going to be solved by a system of equations. We'll figure out unknowns in a second. I want you to remind you that distance is equal to rate times time, and that's what we're going to be using in this problem. So here are my 2 unknowns. For each plane, I do not know the rate, and I do not know how long. Well, I do know how long it flew. I don't know how far it flew. So that would be the distance. But I do know how long they flew, and I do know what the rate is and how far they flew in relation to each other. So let's figure that out. Plane 1, let me see if I can use a different color here. Plane 1, we don't know how far it flew, but we went a distance. We do not know its rate, but we do know how long it flew. It flew for 2 hours. So I'm going to use that as a 2. Plane 2 over here, change my color. We know that it flew at a rate of 80 kilometers per hour faster than plane 1. So I'm going to take plane 1's rate and I'm going to add 80 to it. And we knew that it took off a half an hour after the second plane. So half an hour off of 2 hours is 1.5 hours. So it flew for 1.5 hours. Now, the distance between the two is 3,200 miles. So to find how far the second plane has gone, it's just 3,200 miles minus the distance that the first plane has gone. So now I have my 2 equations in my system of equations here. And as I look at it and try to figure out which way is going to be the easiest way to solve this, I see that the substitution method will be, because the first equation already is solved for variables. It's solved for D, and I want to know what the rates are anyway, because the question was asking me how fast did each plane go. So I'm just going to use my substitution method, and for every D in the green equation, I'm going to put 2R. So here I'm going to put 3,200 minus 2R. Let's see if I can change the color here. In place of D, equals, now if I distribute an hour and a half to R plus 80, then I get 1.5R plus 120. I hope I didn't say 180. I meant to say 80. Sorry about that if I said the wrong thing. Now I'm going to collect all my variables on one side, and I'm going to put my my constants on the other. So if I do that, I'm going to get 3.5R is equal to 3,080. Switch colors here. If I divide both sides by 3.5, then I get my first rate is 880 kilometers per hour. So my first plane flies at 880 kilometers per hour, and my second plane, I know, flies 80 miles faster than that, or 80, not miles, 80 kilometers faster than that. So I'm going to add 80 to my second plane speed, and I get 960 kilometers per hour. And that solves that application problem. I know this video has been kind of long, but I just wanted to go ahead and go through all these examples so we don't have to do them in class. Study them. You will have homework. I'm going to assign it, but it's not going to be due on Tuesday unless you want to get it done ahead of time. I'd like you to start working on it though, so you don't have an abundance of homework that's due on Thursday. But before you do that, I want you to study example 7 on page 458 in your book and example 7 on page 468 in your book. Both of those are application problems, and that's the purpose of this anyway. So you need to go ahead and study those pretty well. And I will see you on Tuesday.